Ladies and gentlemen, welcome to the Academia Sinica Lecture today. Now please welcome President Liao to give the opening remarks.
Good afternoon, ladies and gentlemen. It's a great pleasure for me to welcome you to this afternoon's lecture. And this is our 11th Academia Sinica Lecture. And we are very honored and pleased to have Dr. Shuji Nakamura from UC Santa Barbara to come to give this lecture. Professor Shuji Nakamura was born in Japan, trained as electrical engineering. He's, of course, the well-known inventor of the blue LED technology. And that was a major breakthrough, I would even say, in human history. As many of you know that we have been using the incandescent light invented by Edison for more than a century. And that light has a major problem, meaning that it turns very hot. As you can see that most of the electrical energy is turned into thermal energy. So that's a problem, especially in these days we are so sensitive to the energy we use in the world. So it would be great if we can turn the majority of electrical energy to light energy. And that idea is not new, but it was very difficult to accomplish. So scientists and engineers have invented the other two LEDs, except blue LEDs. The red and green was not a problem, but the blue LED was very difficult to make. Although a small, very dim LED was discovered a few decades ago. But it was not until Dr. Nakamura's development that made this technology practical. So the rest is history. Okay? And this development also illustrated that a dedicated scientist aiming to solve a very important problem in science can eventually be successful. And if you look at his past history, you can easily notice that he didn't really care about publication. He didn't count impact factors, so to speak. And he's focusing on solving real problems. And he did what he wanted to do. So this is a true hero of science, in my opinion. And I'm sure today we have a lot of students and professors gathering here, and many of you are young scientists. And he provides a very good role model for all of us. Professor Nakamura received all his education in Japan. And then he worked in Nichiya company in Tokushima. In 2000, he moved to United States in UCSB. And then he received the Nobel Prize not too long ago, along with two other Japanese scientists. Professor Nakamura also received other awards, including the Benjamin Franklin Medal Award, the Millennium Technology Prize, the Harvey Prize, the Order of Culture Award in Japan, the Global Energy Prize in Russia, in addition to Nobel Prize that everybody knows. So today is our great pleasure to welcome Professor Nakamura. And before we have him give a talk, I would like to invite him up to the stage so we can present him with a gift and also the badge of being elected to the honorary academician of Academia Sinica. Professor Nakamura, please.
Okay. Thanks so much for nice introduction. So today I talked with several scientists here, and several scientists using blue LEDs for the special application. I was so impressed with recent application of blue LEDs. And so today I like to talk about how I could invent blue LEDs, also future solid lighting. So this is just a brief outline. So I talk about the white LEDs and also laser lighting, LED lighting and laser lighting. So at first I introduce myself. So this is Japan now. And Japan is composed of 4 islands, and the smallest island is called Shikoku Island. And so in my case, I was born in Shikoku Island, and I started the Shikoku Island, and just I was born here, fishery village. It's a small, tiny fishery village. This is me, and at the second grade of elementary school, I moved to the old city, and I started here up to high school. After graduation of high school, I joined Tokushima University. This Tokushima University is a local small university, not top-ranking university. In Japan, top-ranking university is Tokyo University, Kyoto University, Nara University. Tokushima University is close to the bottom ranking university. And after getting a master's degree, because Tokushima University has no PhD course, it's a local university. And after getting master's degree, I joined the Nichiya Chemical Industry. It's located in Anan City. It's a small company. Nichiya Chemical is a real pure chemical company. At the time, company's annual sales is $20 million, and the number of employees is 180. And I joined the Nichiya Chemical Industry, so I worked at the Nichiya Chemical Industry for 20 years. It's a small company, and at the company now, this is a pure chemical company, no background of semiconductor technology. So I worked here 20 years, and I had to develop all kinds of semiconductor technology to make LEDs myself. And I could develop blue LED, green LED, white LEDs. And the amazing thing is we didn't do any collaboration with outside the company. We didn't do any collaboration with any universities outside. Also, we never used the outside of money, like the Japanese government. We never used the Japanese government. Totally independently, we developed everything at the local small company. Totally independently. So it's amazing, And so after graduation of the University of Tokushima in 1979, I joined the Nichiya Chemical Industry. So this is my first day at the Nichiya Chemical Industry. So we had the greeting, And he graduated Kyoto University, and she graduated high school. So this sequence is a top-ranking university to high school, Still in Japan, same, They don't care about, their ability. They care about only which university, which high school, graduate. It's ridiculous, And this is, he's the founder, also the president of the company, Nobel. I respect him a lot because he always supported me after joining the Nichiya Chemical Industry, Without his support, I couldn't invent blue LEDs. So I told you, at a remote city, small company, we developed everything independent from outside of the people. And the Japanese academic people became so angry because without any collaboration, we developed everything. So after receiving a Nobel Prize, this time we received a Nobel Prize together with another 2 Japanese scientists. They are Professor Akasaki Amano. And they referred why we got the Nobel Prize, because Professor Akasaki, they said, developed the first blue LEDs, 1989. In my case, Professor Nakamura developed the manufacturing technology of the blue LED in 1993. So manufacturing technology, could you believe? Manufacturing technology. For example, here now among high school students, robot contest is very popular. Robot contest. If one student develops a totally new robot, if one student could develop a totally new robot, he is called the inventor or developer of a new robot. And this is so great. So one company came to him. Oh, we wanted to, make a product of a robot. So at our company, we can do, develop the totally new mass production technology by copying this robot. It's called mass production. Mass production technology means manufacturing. Manufacturing technology is just copying technology, to make a copying a lot of robots. It's companies' work, If this is manufacturing technology, true, all of scientists, engineers who work for the company, maker, they can receive a Nobel Prize in physics, It's a total, all the Japanese people, academics, people cited like this, I am so angry. Because this is a NEDO, New Energy and Digital Development. This is a Japanese government sponsored organization who can give the research funding to university and company. And they say same, 89, basically Professor Akasaki Amano developed blue LED. In my case, 93, I just developed the manufacturing technology, of blue LED in 93. Also, in 95, also at Nichia, we developed the first green LEDs, but no name is written. Also, we developed the first white LED in 96, but no name is written, because because we developed everything totally independent from outside, Also, all of the mass media, newspaper, same. Japanese, this is Japanese newspaper. You can see some people read Japanese, This is, success in development by Akasaki Amano, blue LED developed. But in my case, manufacturing technology, I developed manufacturing technology, Because all the academic people cited like this, so all of Japanese mass media followed what the academic people say, Also, this is the Minister of Education, Minister of Education also same. Congratulations of 3 Nobel laureates. But in my case, the Minister of Education says, same. Akasaki Amano developed blue LED, just I developed the manufacturing technology, And also, this is they refer the, by referring the Nobel Prize Foundation press release. Nobel Prize Foundation press release didn't say anything about the manufacturing technology. Just a Nobel Prize, prize press release is just these 3 guys, invented the high efficient blue LED. That's it. Totally, this Minister of Education lying, lying, Japan. Unbelievable. International 3 Nobel Prize laureate in Japan, like this, after Nobel Prize, all of Japanese media, TV, newspaper, academic people, the master, these academic people, have interest about 7 Nobel Prize laureate, in this government and academic people together. Professor Akasaki development of blue LEDs, in my case, development of manufacturing technology, So this is Alfred Nobel's will. So Alfred Nobel is will. So what kind of people should get the Nobel Prize, This is Alfred Nobel's will. Everybody have to follow this one, his will. So basically, this is at least condition to confer the greatest benefit of mankind. So any research, is contribute a great benefit of mankind. This is at least condition. In the case of a Nobel Prize in physics is this one. The most important discovery or invention within the field of physics. Only discovery or invention, Or in the case of Nobel Prize in physics. No way development manufacturing to get a Nobel Prize in physics, I received, in the past, I received a very prestigious prize, a lot, almost 40 or 50, I received a 40 or 50 award or prize, and for the past, since invention of blue LEDs. all of citation is invention or development of blue LEDs. In my life, this is the first time I received the prize by development of manufacturing technology. That prize was a Nobel Prize. First time. It's amazing, So Japan is a really crazy country, So I'm lucky I left Japan already. So what is LED? So sunlight. So all of the plant and human beings were raised under sunlight. So sunlight is the most friendly light. So basically, our purpose is that we have to copy the sunlight using LED and laser diode. That is called solid lighting. So in the case of LED, so LED is basically composed of 3 layers. So basically, there are substrate. On the substrate, there are N-type layer. Blue layer is called the N-type layer, and the red layer is called the emitting layer. And the green layer is called P-type layer. So basically, we need 3 layers, N-type layer, emitting layer, and P-type layer. So most important is emitting layer, because the emitting layer emits UV, blue, green, red, all kinds of colors by changing the composition of the materials. So after, development of 3 layers in 1993, we started, we developed our first high-efficient blue LED, also started making a product in 1993. So you can say that, I told you, so emitting layer is most important. So emitting layer, we use this material, indium gallium nitride. And by changing the composition of the material, we can make UV to infrared LEDs, just changing this material composition. So we can make UV to infrared LEDs. But, the most biggest market is the white LEDs, using blue LEDs. So white. So how to make white LEDs? Just mix it's white. So this how to make a white color. Just mixing of blue and yellow color, we can make white. Also mixing of 3 primary color, blue, green, red, we can make white. So right now, most popular technique is this one because we need 2 colors, But sometimes we add the red color to increase the color quality. So this is a real white LEDs. So this is a blue LED chip, and the blue LED chip emits a blue light, and this is a yellow phosphor. This yellow phosphor is excited blue light, and this yellow phosphor emits yellow. And the mixing of blue and yellow, we can make white. This white LED has a problem because this blue light directly comes from blue LED chip. So it means spectral width is of blue light very narrow because the blue light directly comes from blue LED chip. So in order to make a good white color, this peak intensity of blue should be very strong. This is just emission spectrum of white LED. So blue intensity is very strong. And the yellow comes from phosphor, so peak intensity is weak, but very broad spectrum. So strong blue peak intensity causes, disrupt the circadian cycle. Basically, blue light, if the blue light enters the human eye, hormone of melatonin is reduced. So melatonin is basically sleeping pill. So we cannot sleep. So nighttime, if you, watch this white LED, you cannot sleep by reduction of the hormone of melatonin. So biggest customer of the white LED is Apple Computer, smartphone company, also computer company. Apple Computer is making the iPhone, iPad, and computer. So all of backlight is white LEDs made by blue LEDs. So this January they did the press release. So Apple moved acknowledges the blue light dangers. The blue spike, strong blue peak intensity in the white light output from electronic device reduces the production of the sleep hormone melatonin and has been linked to various health disorders, including cancer. So very dangerous, So especially for small children, if you have a small children at home, be careful because nighttime they enjoy TV game using iPhone, iPad, also they watch TV, also lighting is now white LED. So everywhere is blue light. So at night time, strong blue light, they can't sleep, and it causes all kinds of health disorder, including cancer. So don't use white LED made by blue during nighttime. Only safe white LEDs, our company's white LEDs. Our company is violet LED. So violet is okay. Right now, violet color doesn't, you can't find any health disorder, this problem. So violet LED is safe. Only blue light causes this problem, blue light. So anyway, using blue LED, we can make all kinds of white or bulb LED light. So this shows the efficiency of the conventional red, green, blue LEDs as a function of the developed years. So basically, red LED was invented in 60s, and gradually efficiency of red increased like this. And after the invention of red LEDs, in order to make any kind of colors, we need 3 primary colors. So we need blue and green LEDs. And since 60s, many scientists all over the world tried to develop blue and green LEDs. But nobody could make it, nobody. But, I told you in Japan, small countryside, at a small company, totally independently, we developed the blue LEDs in 93, green LED in 95, and we developed white LEDs in 96. So basically, independently, we developed everything at the remote city without any help of government, without any help of university, totally independent. So in my case, my history is I graduated University of Tokushima here in 79, and I joined the Nichiya Chemical Industry, 79. And so first 10 years, basically, I developed these conventional LEDs, first 10 years. But Nichiya is a pure 100% chemical company. So the LED is semiconductor technology. So I had to develop all kinds of semiconductor technology to develop red LED from nothing to the real red LEDs for first 10 years, from 79 to 88. But the sales was, but I could make 3 products, but the sales was very poor. Because that already these red LED are already commercialized by in Japan, big company, like in Japan, Panasonic, Sharp, Toshiba, and foreign country, Philips, Hewlett Packard, Osram, all the big companies selling these products. If my small company, chemical company, try to sell these conventional, no way, no name value. So, but I could say small, but sales almost nothing. So, and then 10 years later, around 88, all my, company boss, it's a small company, Every time my boss, every time they saw me, oh, Nakamura, still you work at our company. Why don't you quit the company, immediately, You waste a lot of money to develop that, So they asked me to quit the company. So also I became so angry because for first 10 years, I followed, my direct boss. My boss asked me to work to develop these conventional LEDs. I developed, but the sales was very poor, means I had to take a responsibility, not my boss, I became so angry. So 88, I became so angry. So despite, so I want to quit the company. So before quitting the company, I want to do what I want to do. That is a blue LED research, because after joining the company, I started this red LEDs. At that time, I read all of the scientific papers and patents to develop these red LEDs. All of scientific paper and patent says biggest problem of the LEDs are no blue, no green LEDs. If blue and green are developed, there would be a huge market. So I want to develop a blue LEDs, after joining a company, And I joked with my boss after joining a company, why don't you do the blue LED research, instead of red LED, and my boss said, oh, you are crazy? You know my company. My company has the money? No, zero money. No money. Basically, no funding, zero. And the next, you have a brain? No brain. I just graduated local university, bottom ranking university, no brain. No way. So nothing. At that time, I told at that time, for example, in Japan, like Toshiba, Sony, Sharp, they were spending $100 million to develop blue LEDs for 3 or 5 years. $100 million. In my case, research funding is almost $10,000 US per month. That's it. No way, no? Also, Toshiba, Sony, they formed a project team. They graduated Tokyo University, Kyoto University after getting PhD degree, almost 10 scientists. In my case, just me. I graduated local university after getting master's degree. No way, no? So, after joining a company, every month I joke with my boss, but no way, no? But 88, I became so desperate. So small company, good thing is I could directly talk with my president, company's president and founder. I went to the company's president, founder's office. He was 80 years old, almost 80, more than 80 years old, no? And I asked him, so I want to do blue research, okay? And he said, okay, no problem, you can do it. I thought he was really, Alzheimer's something, to wake up, Oh, you say, okay, so please give me $5 million to do the blue LED research. He said, okay. Oh my gosh, so really, he was really crazy, And I never been to foreign country. Always I stayed the smallest island, Shikoku Island. So I wanted to go to a foreign country. I never been to a foreign country. So I asked him, can I go to the, University of Florida for 1 year? To kind of some research. He said, okay. So, so from 80 to 89, I went to University of Florida for 1 year. Just I wanted to the foreign country. I never been to foreign country. At that time, my age was 35 years old. So, and then 89, I came back to Japan from University of Florida. So I needed only, 3 or 4 years to develop blue LEDs. Very easy. Very easy, just 3 years to develop blue LEDs. The reason is for past 10 years, I worked for conventional LEDs. For LEDs, I had to develop everything from nothing to the blue LED. So I think at that time, I'm the more expert of the LEDs because I had to develop everything, but sales very poor. Just for blue LEDs, I changed the material from this material to this material. And I changed also epitaxial growth method from liquid phase epitaxial growth, MOCB. So basically, other device process, everything same as a conventional LED. So that is the reason I need 3 and 4 years to develop blue LEDs. So Nobel Prize, I got a Nobel Prize only just 3 years research, It's very easy, And also develop green LEDs, that's it. So first 10 years, basically, I developed this one for, red LED. First 10 years, I developed these bulk crystals, gallium arsenide bulk crystals, and substrate, everything from nothing. And epitaxial infrared, epitaxial LED, everything. From nothing, I had to do everything, This is without any small funding. Yeah, so this is, first thing as I worked for this one. So you can see this is a liquid phase epitaxial growth reactor. This is my homemade reactor. I had to, make this reactor myself, everything, because there's no money. But that is contribute a lot to develop LEDs. So next is impact application. So LED, blue, green, white LED used for all kind of application, probably, So interesting, I thought now, in Silicon Valley, most interesting, venture capital interesting is the plant factory. Because for venture capital is worried about, shortage of the food near future. So they invest a lot of money for the plant growth. So plant factory, they use LEDs for light, as a light. So plant means the color is green. So basically, initially I thought only blue and red LED required for plant growth, because the plant green means green light is reflected from plant. But and a lot of advantage of this plant factory, because water use is only 1% compared to outside plant growth, and the yield is very high because everything is automation inside of clean room. And growth rate, no night time, because always LED lighting, no night time. So means the growth rate at least two times. But recently, by controlling the irradiation condition, or 5 times higher than the outside. So 5 times is, in the view of the cost, almost there. And so this is Dr. Tessa Pocock result. So basically, LED 1, 2, 3. This is just they irradiate blue light and red LED light. But the CWF is just he tried to copy the sunlight. You can see a lot of peak. So CWF is basically sunlight, and the LED 1, 2, 3 is just a blue LED light and red LED light, because plant is green. They expected no green LED is okay, but the result is like this. So this is sunlight is best for plant growth. No, blue and red light is not enough. So sunlight is best for plant growth. For human beings, same. Sunlight is best. So right now, all kind of inside lighting is different from sunlight. So, you are every day inside the house, your light is this one. Your growth is like this, be careful. And so this shows the efficiency of the conventional lighting and LED lighting. So basically, Thomas Edison invented the light bulb. This efficiency is only 60 lumen part, 16. And fluorescent lamp is only 70 lumen part. LED, white LED is R&D level is 300 lumen part, but product level is half of this value, so 150 lumen part for as a product, 150 lumen part. So twice is higher than the fluorescent lamp, and 10 times higher than the conventional incandescent light bulb. So by replacing this conventional lighting with LEDs, we can save a lot of energy. Also, lifetime of LED is almost 30 or 50 years, and this lamp is lifetime is very short now. So if you install the LED lamp at home, you don't need any maintenance, And so this is how much energy is saved using LED lighting. Basically, in the United States, by 2020, in 3 years, we can, reduce energy consumption almost equivalent to 19 nuclear power plants by replacing the conventional lighting with LED. But still, LED penetration ratio is, I think, still 20 or 30%. Still not so high, still small. In Japan, penetration rate is very high because I exposure my nuclear power plant. They don't use, nuclear power plant. So due to energy crisis, they have to consider the saving energy. So in Japan, penetration of the LED is very high, 80%. So basically, all over the world, we can save the energy almost equivalent to the 60 nuclear power plant by 2020. So it's a huge energy reduction, So why? So this is next is why it was difficult to develop blue LEDs. So basically, emission color of LED is determined by materials. For blue LEDs, two materials available: zinc selenide or gallium nitride-based materials. And so this is a zinc selenide and gallium nitride. So gallium nitride, you can see, gallium nitride usually grown on sapphire. You can see dark line. This dark line is the crystal defect. Crystal defect. And zinc selenide, you can see no crystal defect, no dark line, no crystal defect. So in the semiconductor, now silicon, IC, LSI, silicon semiconductor, no crystal defect. Crystal defect, 0. So semiconductor technology field, nobody likes crystal defect. So gallium nitride, huge number of crystal defect. So in 70s, 80s, if people tried gallium nitride, people are called crazy, because I talked with Sony scientists. Sony is, working for zinc selenide, and why you select zinc selenide? So I told you in Sony, always project team, blue LED project composed 10 scientists. They graduate Tokyo University, Kyoto University after getting PhD degree. And among 10 scientists, 9 people say zinc cyanide because no crystallized effect. And one crazy guy say, oh, gallium nitride. And the 9 scientists, oh, you are crazy, you are crazy. You have to go back to university to study the solid physics again. You have to read the solid physics again. Nobody likes crystallized effect. Why you say this one? You are foolish. So no way. Other than common sense is that people have to say zinc cyanide. And so in my case, '89, I came back to Japan from University of Florida, and at that time, and I started brewery research. So at that time, basically 1995 of research selected zinc cyanide, only not zero, only less than 1% research selected gallium nitride, but they are called crazy, They are foolish. So in 1992, I attended the Japanese Society of Applied Physics conference. In this field, the biggest conference in Japan is the Japanese Society of Applied Physics conference. So at first I went to gallium nitride session. Gallium nitride session is session chair was Professor Kasaki, and speaker was 2 students from Professor Kasaki, including one of the students, Professor Amano. And so each speaker has 15 minutes. So 2 speakers, after 30 minutes, this session is over after 30 minutes, And then, I went to zinc cyanide session. Zinc cyanide session is always, or at the time, number of audience more than 500. I couldn't enter the room. And this conference continues 1 week, so from Monday to Saturday. So from 9 a.m. to 5 a.m. This session continues one whole month. This session is only 30 minutes, Because I then gallium nitride, because the reason is 91, American company 3M succeeded in making first blue-green laser diode using zinc cyanide-based material, And this is the shortest wavelength ever generated by semiconductor laser diode. So this paper is spread all over the world. All scientists cited this paper. So zinc cyanide is winner, because they could make a laser diode. Laser diode is more complicated technology than LED. So that's the reason 92 like this, in Japan. So 92 all of the Japanese domestic conference is, only for 2,6 material. No nitride, workshop at all in Japan. Anyway, so in my case, I went to University of Florida from 80 to 89. And so 89, for 1 year I stayed at University of Florida. So initially, before going to University of Florida, I was supposed I could operate MOCVD because I went there to learn how to operate MOCVD. But the professor, my advisor said, oh, sorry, I lost my MOCVD, so no MOCVD. Wow, but I came here to operate MOCVD. What should I do? Oh, I have a part of the MOCVD. You can construct the MOCVD, you can use it, So I had to construct this MOCVD with other PhD students, but it took almost 1 year. So I could operate it 1 or 2 times just before going back to Japan. But the good thing is I worked together with the PhD students to develop this MOCVD, and all PhD students, asked me, Nakamura-san, do you have PhD degree? No? I said no, because I had only master's degree, And next, they asked me, have you published any scientific paper? I said, no, I have never published any scientific paper. 0. At that time, my age was 35 years. Then they treated me like a technician. In the United States, if you want to become a scientist, you have to have PhD degree. Without PhD degree, they are called technician. Technician means, just follow what the scientists order to them, Technician doesn't think about anything, just follow what science order, and the size is very small. And 1 year later, I came back to Japan. My dream became getting a PhD degree, not to development brewery, because I never expected I could invent breweries. Just, my dream is just getting a PhD degree, because University of Florida, I experienced a very bad thing, So in that time, we could get a PhD degree by publishing at least 5 scientific papers. It's called a paper degree. We didn't have to go to university, just in Japan, we published more than 5,000. We could get a PhD degree. It's called a paper degree. So my dream became publishing a lot of papers. So I told you there are two materials, zinc selenide and gallium nitride. Zinc selenide is a lot of papers because many scientists all over the world are working for zinc selenide. But gallium nitride, basically in Japan, Professor Akasaki published maybe 2 or 3 papers per year. That's it. No papers. So I thought if I select the gallium nitride, it's easy to publish paper. So that's the reason I selected gallium nitride. But I never thought I could invent blue LEDs. Just after getting a PhD degree, I thought I had to quit the company. But but luckily I could invent blue LEDs. So in '89, I came back to Japan from University of Florida. So I had to develop blue LEDs. So biggest problem, I told you. So LEDs, blue LED basically we need 3 layers: N-type gun, emitting indium gallium nitride emitting layer, and P-type gallium nitride. So at that time, in '89, there are these 2 layers missing. I had to develop these 2 layers. This N-type gun was available since the 60s. So problem these 2 layers. And so '89, I started the blue LED research using MOCVD. So initially, I purchased the commercially available MOCVD. MOCVD used to grow gallium nitride epitaxial layers. And I tried to grow, I purchased a commercially available MOCVD. I tried to grow gallium nitride, but no crystal growth. I tried to crystal growth for a couple of months, no crystal growth. So I was so disappointed. So I thought I had to quit the company. But and then I made a decision. I had to modify this reactor of MOCVD. So since that time, I modified the reactor of MOCVD every morning. Every morning I modify the reactor, and every afternoon I did the epitaxial growth run maybe 5 or 6 times. I continued this pattern 1.5 years. And finally, I developed this MOCVD. I named it 2-flow MOCVD. I developed this 2-flow MOCVD October 1990. So usually MOCVD is just 1 flow because MOCVD we need a laminar flow. If I add additional flow, it's a crazy idea because it's additional flow called a turbulence flow because we need a laminar flow, not a turbulence flow. But I was already desperate, so I added this vertical flow, and then I got best quality of gallium nitride using this technique. I named 2-flow MOCVD. This is the biggest breakthrough in my life. I invented this in October 1990. So this reactor is the best in the world. Since this invention, every 2 or 3 months, I could achieve the breakthrough in this field. Because this reactor is the best in the world. Any crystal growth, crystal quality, best in the world. Any device growth, best device all over the world. So since October 1990, we show the best results all over the world. So since October 1990, every couple of months, I could publish papers because this so reactor is the most important. So first big place is a P-type layer. So P-type layer, So P-type layer, always to obtain P-type gallium nitride, we doped magnesium into gallium nitride. But people doped magnesium since 60s, but always resistivity became semi-insulating when we doped magnesium. But in '89, Professor Akasaki coincidentally found when they irradiate electron beam, they observed the reduction of resistivity, or they got P-type gallium nitride. But they couldn't understand. Also, electron beam irradiation is, nobody can use electron beam irradiation because it scans the 2-inch surface. It takes forever. But in my case, I found just summary annealing. I used summary annealing, and we got P-type gallium nitride. Also, I clarified the mechanism because, hydrogen was, bonded magnesium acceptor. This hydrogen participated magnesium acceptor. But using summary annealing, we can remove hydrogen and we can get P-type gallium nitride. It's called hydrogen participation. So this is P-type problems for past 30 years. It's the biggest mystery. Nobody understands, but I clarified the mechanism. I clarified the physics, but nobody could understand. I clarified physics. But the Japanese academic people say, I developed just manufacturing technology, I clarified the physics, first time. Could you believe Japanese academic people are really crazy, foolish? Next is emitting layer, indium gallium nitride. Emitting layer. So basically in 1889, Professor Akasaki developed this LED structure, just the N-type gun, P-type gun. It's called gallium homojunction. This LED is a gallium nitride, band gap energy is 3.4 eV, means the emission wavelength is 360 number, UV, band-to-band emission, UV emission. This is not blue. In order to make high efficient blue LEDs, we have to insert the emitting layer of indium gallium nitride here. It's called the double-headed structure. This idea was invented by Professor Alfano and Professor Kromer. They received a Nobel Prize in physics, by invention of double-headed structure. So we have to insert the indium gallium nitride emitting layer here to make a high efficient LEDs. But the problem is nobody could make indium gallium nitride. Nobody. But I think, I could use a two-flame MOSFET to grow indium gallium nitride. So in 1992, we could make first indium gallium nitride, which shows a very strong blue and violet emission at room temperature using two-flame MOSFET. This is a real breakthrough, This is an emitting layer. This layer emits blue and green and any kind of colors. So in 92, we solved the problem P-type gallium nitride, also emitting layer problem in 92 using two-flame MOSFET. Just we stacked these three layers, and we could develop the fast high efficient blue LEDs in 92. And for 1 year, we prepared for mass production. And so in 93, we developed we did a big press release of the production of the fast high efficient blue LEDs in 93. Paper appeared in 94. And the Nobel Prize Foundation referred our first high brightness blue LEDs with the double-head structures. And also in 95, we developed a quantum well structure blue-green yellow LEDs. So this is first quantum well-based blue-green LEDs. So now all of LED companies use basically similar structures. Also, we developed a fast violet laser diode. Developed fast violet laser diode. This is used for the violet laser diode used for Blu-ray DVD. Without this invention, nobody could develop Blu-ray DVD. So now this violet or Blu-ray diode could be used for next generation lighting. It's called laser lighting. So this is a three Nobel laureate contribution. So basically, Professor Akasayama developed a buffer layer to improve the crystal quality in 85. Also, they developed fast P-type gallium nitride using electron beam radiation. So in my case, just summarily, also I clarified the physics of the P-type gallium nitride, also emitting layer. So in buffer. So okay, next the UCSB research. Time is over. So UCSB research, we recently, the highlight is that we recently, we developed a tunnel junction. For usually, for LED, for P-type contact, people use ITO, ITO. And, but recently we developed a tunnel junction. This is Professor Jim Speck's idea. He just proposed, why don't you use MB to make a tunnel junction? Because in that case, no hydrogen participation of P-type layer. This was too much, Just I show the result. So this is result. So this is currently commercial available blue LED is efficiency is around 40%. 40%. But using a tunnel junction, we could increase almost double the efficiency of the current incorporation commercial available blue LEDs. This is amazing, All of LED companies spend maybe past 20, 30 years to increase the efficiency from the 10% to the 40%, But now at the UCSB, student found just using tunnel, we can suddenly increase the efficiency double. So, still we have to do the voltage, but almost double. It's amazing, This just is tunnel junction. This is a great result. And the next is second generation of GaN LEDs. So first generation is grown on sapphire substrate. Always the LED grown on sapphire substrate now, but second generation is grown on gallium nitride substrate. It's called GaN-on-GaN. So I moved to the United States in 2000 because Japan was very boring. Because because I think for me, Taiwan and the US are very similar. Everybody want to do your own company, start a company, no? Everybody here in Taiwan and America, it's very similar. In Japan, nobody interested in starting a company. Everybody interested in only joining a big company, no start company in Japan. But Taiwan and US are very similar. Everybody wants to start a company. So I moved to the United States and in 2000. And the first week at my office, always my phone is ringing. I took a phone and all the phone call from the venture capitalists. Venture capitalists, oh, you're a professor now? Yes. Oh, why don't you start a company, Oh, yeah. And finally, we started the company, in 2008. Because, we got a great result of GaN-on-GaN LEDs in 2006, with Jim Speck and Professor Steve Demos. So we started the company in 2008. Company name is Solar. And this company is, we use violet LED to make white LEDs. Because using violet, we expected the white color quality of white should be much better than white LED made by blue. So that's the reason we start the company using violet LED to make white. So now we are making all kind of white LED lamp using violet LEDs. And also chip shape is used as rectangle shape, but we use a triangular shape to increase efficiency. Also, these are our violet LEDs. Violet LEDs efficiency is 75%. The commercially available LED only 40%, almost twice, no? It's good, no? And so GaN-on-GaN is no defect, crystal defect. So currently blue LED, green LED, a lot of crystal defect because these gallium nitride grown on sapphire substrate, different substrate materials. I want to give this one. So big difference of the white LED made by violet is all visible color, blue, green, red color come from phosphor. These phosphors are excited by violet LEDs. So big difference is blue, green, all visible color come from phosphor. That's a big difference. So this is most important view graph. You can see. So if you have small children, please watch this one carefully. This is the most important result. So daylight is sunlight. Sunlight is, all visible color is a full spectrum, no missing color. Also, UV and the infrared emission. This is sunlight. Sunlight is the best light for human being. Also, plant growth, I told you. Halogen and the conventional incandescent bulb same. So, full color spectrum. So, conventional lighting is also healthy light. The problem is currently commercially available white LED made by blue. Almost 95% of commercially available white LED is this one. Blue LED excited yellow or some red phosphor. So no violet, no blue green, no deep red. This is a 95% white LED, this one. Taiwan, I think almost 100% white LED, this one. You can see this one totally different sunlight. Totally different sunlight. I show the plant growth. Plant growth, this is plant growth normal growth. Under this light, I don't know what kind of plant growth happen. So this light is you are at home. And solar's white LED is violet LED except blue, green, red, phosphor. So full color spectrum, no missing color. So among white LED, only this one is same as sunlight. So if you have small children, you have to think about what kind of light, LED light you have to use at home. This is, considered plant growth, I cannot recommend. And also, this is also the white. So all kind of white paper, white shirts include the brightening agent. It's a fluorescent material. This fluorescent material can be excited by violet or UV, not blue. So all kind of, is white LED made by blue. All of white color become yellowish color. Like white, T-shirt, white shirt, you wash many times, always yellowish color. If the light is white LED made by blue, but solar and violet excited this brightening agent, so it's white, And so this is the current commercial available white LED, just blue, strong blue peak and yellow color. This currently commercial available white LED made by blue. So this blue region, this highest circadian sensitivity. So this wavelength region cause a health problem, reduction of hormone. You know, so if you blue, it's called all kind of health problem. You can't sleep. But morning and daytime is okay. Especially morning, when wake up, we need the blue. But nighttime, it's a problem. After nighttime, you use this white LED, you can't sleep. But the solar zone is violet, so not this region, so it's okay. Using violet, we can make white without any blue. So it's very safe. Nighttime, you have to use this one. You know, if you use this one, it's called all kind of health problem. And also, so recently, you know, this currently available white LED, there is blue and yellow. And recently, you know, like iPhone, you have iPhone, there's night mode. You push a night mode is just, they reduce the blue intensity. So in that case, reduce the blue intensity, it's become yellow, no? But the solar one is just use violet, no blue intensity, and still beautiful white, you know? So recently, this Helia bulb lamp. This is a Helia bulb lamp is, you know, basically for, it's automatically controlled. If the morning, automatically it becomes blue intensity strong, and daytime is blue intensity so-so, and nighttime, no blue intensity. So automatically this control, no? This is good. Okay, third generation lighting is laser lighting. So basically, you know, this shows the efficiency of blue LED and blue laser diode as a function of current density. So basically, blue LEDs, with increasing current density, efficiency becomes very small. So at this current density region, no efficiency, no blue emission. But the laser diode, blue laser diode at high current density, still efficiency very high. So in order to make a 60 watt, conventional 60 watt incandescent equivalent with brightness 1,000 lumen, in the case of LED, the emitting area is become very huge because you know, current density always almost close to zero, means the emitting area should be very large. But in the case of laser diode, the current density is very high, 1,000 times higher than LED, so we can use a tiny chip to make the same brightness of the lamp. So, you know, so it means, you know, in the future, we can reduce the cost, system cost of the laser lighting. For example, you know, to irradiate this room, we need a lot more LED lamp. But in the case of laser lighting, we need a small number of lamp. So, no. I don't see. So we are developing at the UCS, we are developing high power blue laser diode. I won't skip this one too much. And also we are developing big cells, you know, too much detail, you know, big cell. So currently big cell is conventional big cell is direction polarization random, but using a non-polar big cell array, we can control direction polarization. Also LED and laser diode is you know, interesting for the next generation communication. So now everybody enjoy internet, no? Using Wi-Fi. But the Wi-Fi, you know, internet is Wi-Fi. Wi-Fi is everybody, you know, Wi-Fi is many people are using Wi-Fi. So capacity is almost saturated. So next, you know, communication should be Wi-Fi using visible light communication by modulating LED lighting or modulating laser lighting. Their data rate is, in the case of LED, is 10 times higher than the Wi-Fi, and laser Wi-Fi is almost 1,000 times higher than the Wi-Fi. You know, so using this technology, you can download the big data immediately. You know, speed much faster, you know? So, you know, so just modulation, we modulate these LED lighting at very high speed. And so, you know, Wi-Fi means we use radio frequency. You can see radio frequency, only small portion is allotted to the Wi-Fi. It's limited. And, but everybody uses Wi-Fi now for internet, data demand like this. It's almost saturated. But the visible light communication, Wi-Fi is like this, lot of advantage, no limitation, And especially for laser lighting, laser diode is already used for communication, plastic fiber and underwater communication, also satellite communication, all kinds. So this shows modulation boundaries. As LEDs are basically, megahertz order modulation speed, because carrier recombination speed like this. But by minimizing the chip size of LED, we can minimize the capacitance. We can increase the close to gigahertz, but still megahertz order. But the laser diode is commercial laser diode easily more than 2 gigahertz, well, much faster. So this is LED white LED, and this laser diode white light, laser lighting. So laser lighting is much faster, 2 gigabit. So data translate is 2 gigabit per second. It's much faster. So this is modulation boundaries, the function of wavelengths, and you can say. So LED is less than 1 gigahertz, because LED is basically this modulation speed determined by carrier lifetime. Carrier lifetime only nanosecond order, so this is a limit. But the laser diode is modulation speed picosecond. So it's a gigahertz, and especially for UCS, we recently use simpler. We achieved the 5 gigahertz. But this is limited by the photodetector, because right now no photodetector which can detect more than 5 gigahertz, and so laser lighting future. So already laser high power blue laser used for these projector. If we use a high power blue laser for projector, this projector becomes TV, 100-inch TV, 4K TV, and also pico projector. Pico projector, interesting is we using a high power blue laser diode. We can make the 50-inch, 60-inch TV using a small box. This small box is connected to smartphone. So if you carry the smartphone, you can also carry the 50-inch, 60-inch TV. So it becomes same as a mobile phone, smartphone. With a 40, 50-inch TV become mobile because using high power the diode. It's a small projector. Also, automobile headlamp. Automobile headlamp. So right now, automobile company use LED headlamp, but using laser lighting, irradiation distance become, I think now up to 1 kilometer. In the view of the safety, this is much safer, Especially China also same. China is long highway, They need this one, In Japan, we don't need this one because the Japan highway is like this, This is enough, but for safety, this one is much better, So laser lighting is better, And so especially German cars, they use automobile headlamp. Automobile headlamp, they use laser lighting because Germany, outbound, there's high speed, highway, outbound. So they need the safety, so they have to use laser lighting. And so this is, okay, BMW. I got email from this company. When I received some award, I don't know, this is inventor for something, something. So and BMW sent me email. So and congratulations receiving the award. And he said, so email said, oh, we can give you a free i8. This is i8, free i8, This price is $200,000 US, And wow, I can get free. Oh, yeah. And so, but I'm native English speaker, so my English is not so good. So I transferred my email to Steve Denvers, and Steve, please check this email. This email says I can get a free i8, $200,000 US, Steve says, oh yeah, you were right. Congratulations, you got a free i8, $200,000 US. Wow, But Steve is not about person, And I transferred the email to Paul. Paul is a very strict person, And Paul says, Oh, yeah, you understand wrong. This is you can enjoy free riding, you know, free riding. So they brought a car and just we can enjoy free riding. That's it, you know. The big difference, you know. Okay. So this is our UCSB Solid State Lighting Energy Electron Center. So we have this center is you know, through this center we collaborating 13 companies. And main professor is Professor Jim Speck, Professor Steve Denbers, and me. And this professor are working to develop the next generation LED lighting and laser lighting. We are working together, you know, always. And Mesh Mishra is developing the gallium nitride with high power electron devices, you know. And Chris Van der Waals work for the theory. And this is during, you know, Chancellor Henry Young's wife. I don't know, Henry Young disappeared somewhere. And others are basically PhD students. About 40 PhD students are involved in this center to develop all kinds of nitride-based devices and crystal growth, you know. And this is a UCSB campus, you know, UCSB campus like this, you know. Along UC campus along a beautiful beach, you know. The problem is, you know, always every year students enjoy the, you know, university, what's that, festival? Oh, yeah, some kind of festival, no? They crazy, every year they enjoy crazy party, no? And basically through crazy party, always one or two students they dying, no? Because they jumped from the top of the dormitory to this beach, you know? They definitely die after enjoying a drinking, drug, you know. So every year, you know, police officer make a barricade to ban the, you know, this crazy party. But always the students enjoy a crazy party, you know. It's a problem. Okay, that's it. Thank you.
Well, thank you very much for the wonderful talk. We can take a few questions from the audience, if there's any. Yes, please. Yes, in front of you. Push the button.
I would like to ask the Mukamura-san, I have a question. I might be the first one to use Nichia white diodes in 1997. I started the LED lighting since that year. And since that, I found some big change in environments, especially. I don't know whether if you would like to share your knowledge with us, how do the biochem compound affect to us, both in ecosystem? Because you know that we human eyes can sense 3 colors, but for the other animals, they have 4 colors, especially the blue light. Because I saw the environment has a huge change.
Oh, environment a huge change means using LED lighting?
Yes. Blue light. Because our human beings are very sensitive to blue light.
Yeah, so it means blue light pollution? You're talking about?
Yeah, and not only the pollution, and the lighting, and also the botanic, you know, the plant, they all need green light and blue wavelengths. So especially, you know, as this I found something really wrong, especially when I was in Amsterdam, because, you know, Holland is an agricultural country. And I found out something really wrong because the birds fly in the night, disturb their sleeping hours. Yeah.
Yeah, so I told you, so blue light causes all kind of health hazard. If blue light is for nighttime. Also, plant growth, same. Plant growth, sunlight is best. So basically, if nighttime we use the blue light, it's called blue light pollution, or blue health hazard. So don't use blue light for nighttime. So please use violet LED. Yeah. So in that case, I don't think at this moment we don't see any problem. Right now.
I'm very curious of your second generations. You know, that's again this full spectrum diodes. I mean chips. I'm really very curious. I don't know whether if I can get more information from you or not, because I heard this last year when I was in Frankfurt. Because I saw Philips, they have light for, that's a botanical, that's a plant factory. They grew the vegetables indoors, and in London, the undergrounds. So I don't know whether this new gain-on-gain, these chips, is effective.
Yeah, already
or not.
commercial available. Just check my company's website.
Solar.
Yeah, you can find
saw
other
that.
product. Yeah.
Yeah.
I don't see any problem. And also, recently, in Japanese eye doctor found, a lot of myopia. Myopia is nearsighted eye. For nearsighted, nearsighted eye, myopia. So all of children right now, especially Asian country, all of children have myopia, nearsighted eye. Everyone has glasses, children.
Yeah.
But 40 years, 50 years ago, only 10% children had myopia, no glasses. Because 40, 50 years, when we were children, we were always playing outside under sunlight. Under sunlight, no myopia. And this doctor studied the sunlight, which wavelength is contributed to prevent myopia. And he found violet. Violet light prevents the myopia. So because right now inside, if people stay inside, children inside, no violet light at all. But so now violet light is very important to prevent myopia. And so please, in that case, please use solar white LED because violet is included.
So do you think that we have to be really very careful to say if we want to use the LED,
yeah, blue light, especially nighttime, blue light causes all kinds of health problems. So that is all doctors find out. So nighttime, but morning, daytime, blue light is a good light. Morning for wake up, we need blue light, and daytime we need blue light. But nighttime, because nighttime blue light is a hormone of melatonin, we can't sleep. This problem, it's called all kinds of health problems.
Because I'm doing some research with the state government about this, and I'm really curious of that because I don't want the, that's LED lighting damage our human beings and even ecosystems.
Let's have another question after answer this. Any other questions from the audience? Yes, please. Someone in the back.
Thanks for the nice lecture. My question is that as you mentioned in start, like when you start your research, the inventing blue LED was the biggest challenge. So my question is like, what do you think, what is the biggest challenge in current progress of solid state lighting?
Biggest challenge of the current solid state lighting?
Yeah, in progress to achieve this like solid state lighting. The biggest challenge in the current time.
Current biggest challenge of solid state lighting. I think what's it? Still for general people, LED lighting is too expensive, not expensive. Because conventional incandescent bulb lamp is 50 cents, But now is LED bulb lamp is $2, four times expensive. But it's a misunderstanding problem because using LED bulb lamp, we can reduce the electricity bill dramatically. So basically, maybe a couple of months later, we can make a profit by reducing electric bill. So for even the initial purchase is expensive, but a couple of months later, they can make a profit by reducing the electric bill. Thank you.
Okay, let's thank Professor Nakamura again. Very nice lecture. Thank you very much.